Okay, in this lecture we are going to continue with example 53. We are looking at the graphical method for solving a linear programming problem, and we are specifically looking at the corner point method. So the LP problem we have on this slide, we have the objective function that we would like to maximize, and then we have the constraints. In the previous lecture, I showed you how to set up the feasible region for this specific example. And we got to this area here as the feasible region. So in this lecture, we are now going to continue with this one, making use of the corner point method. Now, if you look at this slide here, or this graph, you will see that we have 4 corner points here. I'm going to number them. I'm going to number them A. So this corner point here is A. Then this one here will be corner point B. Then this one here, that corner point there, is C, and this one here I will call corner point D. The order in which you number them does not matter, but just to continue with this example, I'm going to number them in this order. Okay, so you also have this graph in your notes. So there again you can see your 4 corner points, and now we want to, for the corner point method, we want to evaluate the objective function at all the corner points, in this case at the 4 different corner points. And because we want to maximize the objective function, we want to find the corner point where the objective function is maximized, and that will then give us our solution. For an LP problem, your solution will always lie at one of the corner points of your feasible region. Okay, so first of all, we are going to find the x1 and x2 values for corner point A. Now, if you look at corner point A, we know that x1 is 0 because it lies on the x2 axis. So x1 must be 0, and x2 in this case must be equal to 60 because that is the line x2 equal to 60. So for corner point A, let me just do that on the next slide. For corner point A, we know that x1 is 0 and x2 is equal to 60. So that's my first corner point. Now let's go to corner point B. Now that is corner point B, and that is where my constraint, and that blue line was my second constraint. Perhaps I should also number my constraints. So this blue one was my second constraint. I'm referring to this as my second constraint. This one is my first constraint, and that one is my third constraint. So if we number those constraints on the graph, that's my second constraint. The red line here is my first constraint, and then the purple one here is my third constraint. Okay, so corner point B is where the second constraint, or the second equation, where it intersects with the x2 axis, and that was equal to 90. So we now know that, again, my x1 will be a 0 there, and my x2 is equal to 90. Then if we go back, I'm going to skip C just for the moment, and first look at corner point D. Now, corner point D is where my constraint 1, the red line, and constraint 3, the purple line, where those three, or rather where those two intersect. We know that line 3 is where x2 is equal to 60. So at least we know what the value of x2 is, and we would like to find the value of x1. Okay, so for corner point D, we know that that is where constraints 1 and 3 intersect. 1 and 3 intersect. Now, line 3 is where x2 is equal to 60. And to find the value of x1, we will substitute x2 equal to 60 into the equation 1. Now, my equation 1, let's just quickly remind you what your equation 1 is. Equation 1 is this 10x1 plus 8x2, and if we set it as an equation, it is equal to 800. So I'm going to substitute x2 equal to 60 into that equation. Now my x2 I substitute with 60. So that gives me 10x1 equal to 800 minus 8 times 60, which is 480. So that is then equal to 320. So x1 would be 320 divided by 10, which is equal to 32. So for corner point D, my x1 is 32 and my x2 is equal to 60. Okay, and now we only need to find corner point C. Now if you go back to corner point C, you will see that corner point C is where equation 1 and 2 intersect. So to find the values of x1 and x2, we have to solve those two equations simultaneously. So that, just to remind you, this is my equation 1 and this is equation 2. If I substitute the less than or equal to with equal to signs, we call them equations, and we have to solve those two simultaneously. Okay, so that is what I'm going to do then. This is equation 1. Okay, and there are different ways to solve this, but what I am going to do is I am going to take equation 1. So this is my equation 1, this is my equation 2. I'm going to take equation 1 and I'm going to subtract from that 2 times equation 2. The reason for that is I want this x2 term to fall away. So if I do that, I will get 10x1 and then I subtract from that 2 times equation 2. So 2 times 3x1 will be 6x1. 2 times 4x2 will be 8x2. And then, sorry, that is an 800. And then 2 times 360 will be 720. And if I subtract them, I get 10x1 minus 6x1 is 4x1. 8x2 minus 8x2 will just give me 0. And that's what we are trying to do. We want one of the terms, the x1 or the x2 term, to fall away. And then 800 minus 720 will give me 80. And from this, I can solve that x1 is equal to 20. So now we know that x1 is equal to 20 and we have to find the value of x2. So to find the value of x2, I will substitute x1 equal to 20 into either equation 1 or equation 2. So I'm just going to substitute it into equation 1. So we have solved that x1 is equal to 20. So I get 8x2 is equal to 800 minus this 200. So that's 600, and that will give me x2 equal to 75. So now I know that at corner point C, my x1 is equal to 20 and my x2 is equal to 75. So for corner point C, I have that x1 is equal to 20 and x2 is equal to 75. So now I have the coordinates for all 4 my corner points, and I will now substitute these corner point values into my objective function. What is the objective function again? This function here is my objective function, and I want to maximize my objective function. So I will substitute the x1, x2 values for my 4 corner points into that objective function. Okay, in this slide, you can see for corner point A, my x1, x2 coordinates are 0, 60. I substitute it into my objective function to give me 16,200. Then for corner point B, I substitute x1 with a 0 and x2 with a 90 to get 24,300. For corner point C, the one that we solved last, my x1 is 20, my x2 75. I substitute it into my objective function and I get 24,250, and the same for corner point D. And because we want to find the objective is to maximize the objective function, you will see that the maximum is at point B. So now we can say the optimal solution is at the point x1 equal to 0 and x2 equal to 90. It's because that is where my objective function is maximized, and the maximum value of my objective function under these constraints is then 24,300. Okay, so the corner point method works very similar to the level line method we did previously. We find the feasible region by graphing or plotting our constraints, and then instead of working with a level line, we find the coordinates for all the corner points on my feasible region, and then we substitute the corner points into our objective function, and we find the optimal solution. Okay, just a few hints. Always clearly identify the feasible region and make sure that your feasible region is indeed correct by substituting any value within the feasible region into all your constraints and making sure that those constraints are satisfied. It is much easier if you label your axes and your constraints clearly in your feasible region. That will help you to identify your corner points and to evaluate your corner points so that you can find your optimal solution.